Hi everyone, I'm Will Rosenbaum and I'm excited to talk to you today about my joint work with Jukka Suomela entitled Seeing Far versus Seeing Wide, the Volume Complexity of Local Graph Problems. Here's a quick outline of my talk. I'll start by describing the motivation for this work and give a high-level overview of our results. Then I'll move on to discuss the volume model that we introduce in a little bit more detail. I'll describe one problem our paper analyzes in detail called leaf coloring and explain how it gives one of our main results. Finally, I'll conclude with open questions and avenues for further research. I'll begin by describing the context for our work. The starting point for this work is the local model of distributed computing. The local model is a synchronous message passing model with no bandwidth restrictions. In this model, in T rounds, each node sees its T neighborhood and makes computational decisions based on that information. The main complexity measure is distance, how far a node needs to see in order to produce its output. Here's an illustration of the local model. At the beginning of an execution, a node only knows about itself. After a single communication round, it sees its neighbors. In the next round, it sees its neighbors' neighbors, and so on. After 5 rounds, the central node sees the entire network. In our volume model, each node adaptively queries its neighborhood. In T rounds, each node V can query at most T nodes. Each new query must be a neighbor of a previously queried node. Thus, the set of queried or visited nodes form a connected component containing V. The main complexity measure is the maximum number of nodes queried by any node V, a measure we call the volume. We note that the volume model is very similar to stateless LCA, local computational algorithm, or the cent local model. The main difference is that we think of each node as executing the algorithm independently in parallel, whereas the LCA model, there is a centralized algorithm performing the queries. In particular, the queries made by a node in the volume model must be neighbors of visited nodes. Further, we assume that each node has access only to local randomness, while in the LCA model there is shared public randomness. Here's an illustration of the volume model. Again, at the beginning, a node only knows of its own existence, its ID, and its degree. In a single round, the central node can query one neighbor. In the next round, it queries another neighbor, and so on. Each new query is a neighbor of a previously queried node. After 5 rounds, the central node sees only at most 5 nodes in the network. Why do we introduce this model? Why do we feel that volume complexity is an interesting complexity measure? The first reason is that we believe the atomic single node queries are natural in several contexts. Many APIs limit the number of requests that an algorithm can make to a data structure. For example, the Facebook and Twitter APIs are limited to several hundred queries per user per hour. Thus, the total number of queries per user is an important measure of complexity in practice. Another reason that we are interested in the volume model is its connections to massively parallel computation, or MPC model, which is used to understand frameworks such as MapReduce and Apache Spark. The following lemma formalizes this connection. Any protocol with volume vol can be transformed into an MPC protocol using O of vol rounds and space O of vol plus n to the c plus delta for any constant c greater than 0. Thus, understanding volume complexity could have valuable ramifications for massively parallel computation. With this motivation in mind, our main goal is to understand the volume complexity of problems in distributed computing. In this work, we focus on locally checkable labeling problems, or LCLs. LCLs are characterized by the following properties. LCLs are defined on bounded degree graphs, so we only consider graphs where there is a fixed constant upper bound on the maximum degree. There are a finite number of input states and a finite number of output states for each node. Finally, correct solutions can be verified locally. That is, once the outputs are determined, each node can verify the correctness of the solution by examining a constant radius neighborhood around itself. A solution is globally correct if and only if the solution is correct in a neighborhood of each node. Many of the classically studied distributed graph problems are LCLs. For example, proper coloring, maximal independent set, and maximal matching are just a few examples. Finally, LCLs have recently been very well understood in the local model. These recent results give us a good jumping off point for the sort of questions that we would like to ask about the volume model, and as well as some ideas of tools that we might apply in order to understand volume complexity. So here's a brief overview of what is known about LCLs in the local model. In the past 4 years or so, this striking and surprising picture has emerged for the complexity of LCLs in the local model. All LCLs fall into one of 4 complexity classes. The first class, that we have labeled A in the lower left-hand corner, consists of problems whose deterministic and randomized distance complexities are O of 1. In the figure here, the x-axis denotes the deterministic distance complexity of a problem, and the y-axis is the randomized distance complexity. The second region, labeled B, is the so-called symmetry breaking region, and contains problems such as delta plus 1 coloring. These problems all have distance complexities between log star n and log star n, both deterministic and randomized. The third region of complexity classes of LCLs is the so-called graph shattering region. It contains problems such as the constructive Lovász local lemma and sinkless orientation. This is the only region where randomness can give an exponential improvement in the distance complexity of a problem. Finally, region D is for global problems. These problems have randomized and deterministic distance complexities that are both at least log n, and randomization is known to help only polynomially. The takeaways from the previous work are that there are 4 distinct regions of distance complexity classes: the local region, symmetry breaking, graph shattering, and global classes. Randomness only gives superpolynomial improvement in the graph shattering regime. The main question that our work addresses is, does volume complexity obey a similar pattern? Our main results are that in the local and symmetry breaking regimes, problems are similar in the volume and local models, but in the global regime, volume is fundamentally different from distance complexity. In particular, there are problems exhibiting many different trade-offs between randomized and deterministic volume complexities, even when restricting to problems with fixed distance complexities. This figure illustrates our results for the volume model. On the right is the randomized and deterministic distance complexities, as in the previous figure. On the left, we illustrate randomized and deterministic volume complexities of problems. Each edge between nodes represents a problem whose complexities are indicated by the position of the nodes. Thus, there are 4 dimensions being illustrated here: deterministic distance, randomized distance, deterministic volume, and randomized volume complexities. For example, if you look at the edge between log n on the right side and n to the 1/4 on the left, right here, this indicates that there is an LCL problem whose randomized and deterministic distance complexities are both log n, while its deterministic volume complexity is n, and its randomized volume complexity is n to the 1/4. The main takeaway of this figure is that volume complexity looks very different from distance complexity. Randomization can make a huge, even an exponential difference in this regime of global graph problems. For distance complexity, there are no such separations between randomized and deterministic complexities in the global regime. Additionally, it's somewhat surprising that even if we restrict to a class with fixed distance complexity, say log n, there can be infinitely many different randomized volume complexity classes. Now that we've seen an overview of our results, I want to go into a little bit more detail describing the computational model. As usual, we denote a graph by G equals VE. Each node has a unique identifier, and each edge has an associated port number for each of its endpoints. The nodes represent processors, and each node maintains a set V sub V of visited nodes, where initially V sub V only contains V itself. At the beginning of an execution, each node only knows its ID and degree. Each round, each node queries a single node, U, that is a neighbor of some previously visited node, W. Upon querying the new node U, V receives U's ID and its degree, and U is added to the set V sub V. The queries are adaptive, so future queries can depend on the responses to previous queries. When discussing randomized algorithms, each node has its own private randomness. This randomness is visible to visitors. That is, when a node V queries another node U, V sees U's random bits as well. In particular, this assumption means that after V queries U, V can simulate U's behavior. The volume cost of an algorithm is the largest number of queries made by any node in the network. We take this maximum over all graphs on n nodes and input labelings on these graphs. A few questions that we consider are, what are the possible volume complexities of LCLs? How are volume and distance complexities related? And what is the role of randomness in the volume model? Before delving into our main results, I want to give some simple observations about volume complexity. First, the volume complexity of a problem is always at most its distance complexity. On the other hand, volume and distance complexities are at most exponentially separated. This is because we consider only bounded degree graphs. If G has maximum degree at most delta, then the size of each node's radius R neighborhood is at most delta to the R. Trivially, a problem's randomized complexity is at most its deterministic complexity. For LCLs in the local, that is distance model, Chang, Kapelowitz, and Petty proved that the deterministic distance is at most exponential in randomized distance. Their proof carries over to the volume model as well, so randomized and deterministic volume complexities are at most exponentially separated. These observations give bounds on the separation between distance and volume and between randomized and deterministic volume. Our results show that all of these bounds are the best possible, and we exhibit a rich, infinite family of complexity classes between the upper and lower bounds. I'll now give some details for one problem, leaf coloring, that exhibits the largest possible separation between randomized and deterministic volume complexities. I'll also briefly mention two other problems giving other trade-offs. In the leaf coloring problem, the input to each node consists of a left and right child, a parent, and a color, red or blue. A node with two non-empty children is said to be internal, and all other nodes are leaves. The output of each node is as follows. Each leaf simply outputs its input color. Each internal node should output the same color that one of its children outputs. Here's an illustration of an input for a leaf coloring. Again, the output coloring for the leaves consists of their input colors. Each internal node should output the same color as one of its children. Such a coloring can easily be found greedily. And here's a valid output coloring. It is important to note that while the graph in this case happens to be a tree, the input doesn't need to be a tree. There is some subtlety in dealing with the case where the input graph is not a tree, as the subgraph consisting of cycles from parents to children contains a cycle. Let's analyze the distance complexity of leaf coloring. That is, the complexity in the local model. The deterministic and randomized distance complexities are both O of log n. To see this, observe that each node is within distance log n of some leaf. Thus, each node can look at its neighborhood until it finds its nearest leaf. The node outputs the color of its nearest descendant leaf, choosing the leftmost leaf in the case of a tie. This is easy to see that all nodes along the path to the nearest leaf output the same color, so this procedure solves the leaf coloring problem in O of log n distance. For the lower bound, consider a balanced binary tree. The root is at distance log n from its nearest leaf. It is straightforward to show that the root cannot output correctly if it doesn't query any leaf. If all leaves are colored, say, red, the root must output red. But the root cannot distinguish the case of all red leaves from the case of all blue leaves without querying a leaf. Thus, distance log n is necessary to solve leaf coloring. This lower bound also applies to volume, since volume is at least the distance complexity. Now let's look at a randomized volume upper bound. I claim that the randomized volume of leaf coloring is also O of log n. Here's the algorithm. Each internal node chooses a random child using its local randomness. Nodes then follow the path of chosen children until reaching a leaf. After O of log n steps, every node reaches a leaf with high probability. Then each node outputs the color of the leaf it reaches. All nodes along the path follow the same path, so they output the same color. Thus, this procedure solves leaf coloring. I'm lying a little bit because the node could encounter a cycle, but this case is straightforward to deal with. If a node encounters a cycle, it simply chooses the other child of the first repeated node it encounters. Here's an illustration of the algorithm on the same input that we saw before. We start with the same input coloring. First, each non-leaf node chooses a random child. Then each node follows the path of chosen children until it reaches a leaf. For example, if we look at the root here, it's going to follow the path down to this blue node and output blue. And sure enough, that's the output that the algorithm finds. With high probability, all paths to the leaves have length O of log n, so this procedure has volume complexity O of log n. The correctness follows because all nodes along a directed path reach the same leaf and therefore output the same color. In particular, every internal node outputs the same color as one of its children. It is important that we use local randomness when choosing a child. That is, when a node V arrives at another node W, V uses W's randomness to choose the next step, thus ensuring that V and W choose the same of W's children. As a final note, there's still the subtlety of dealing with cycles, but again, this doesn't pose much of a problem. We now consider the deterministic volume complexity of leaf coloring. We claim that there is an omega of n lower bound. To see this, fix any deterministic algorithm A and a node V executing A. We can adversarially construct an input G that is a binary tree such that A never queries a leaf, so long as A uses fewer than n over 3 queries. We then complete the tree with leaves, all of which have an input color that is the opposite of whatever A outputs. Thus, A does not correctly solve leaf coloring on this instance. So just to summarize, we've shown that the randomized and deterministic distance complexities of leaf coloring are theta of log n. The randomized volume complexity is also theta of log n, but the deterministic volume complexity is omega of n. The moral is that randomness can help exponentially for volume in the global problem regime. This is in contrast to the distance complexity, where randomization can help at most polynomially. Briefly, I'll mention two other problems that we discuss in the paper. We call the first one balanced tree labeling. For this problem, each node in the tree must decide if the subtree rooted at it is balanced. We show that the distance complexities for this problem are theta of log n, while both the randomized and deterministic volume complexities are theta of n. This problem gives the maximum possible, that is exponential, separation between distance and volume complexities. The second problem is called hierarchical 2.5 coloring. Here, nodes must perform a certain coloring task. The original problem was analyzed by Chang and Petty, who showed that randomized and deterministic distance complexities can be made n to the 1 over k for any positive integer k. We showed that a variant of this problem has the same distance complexities, and the randomized volume complexity is also n to the 1 over k. But again, the deterministic volume complexity is theta of n. I will conclude by discussing 3 open questions that we pose in this paper that I think are especially interesting. The first question concerns deterministic complexity. Are there LCLs with deterministic volume complexities between log star n and omega of n? All of the problems that we consider have deterministic volume complexity omega of n. We would like to know if this is inherent to the model or if there are some other problems with intermediate deterministic volume complexities. Another question that we have concerns the graph shattering regime. Recall that these problems have deterministic distance complexity theta of log n and randomized distance complexities poly log n. A canonical problem in this regime is the sinkless orientation problem, where the goal is to output an orientation of all edges that doesn't contain a sink. That is, no node has all edges oriented towards it. What are the possible volume complexities of graph shattering problems? The final question concerns the type of randomness that we use. One could envision at least 3 reasonable ways of using randomness in the volume model. The first is public randomness, where all nodes share a common random string. The notion that we use, we call private randomness. Here nodes have their own randomness, but whenever a node is queried, its randomness is visible to the algorithm querying it. A weaker form of randomness is secret randomness, where each node has its own randomness that's invisible to visitors. The final question we pose is, what is the complexity landscape for these different types of randomness? How does the randomness affect the complexities of different problems? We suspect that public and private randomness are probably comparable in their computational power, at least for solving LCLs. We believe that secret randomness is significantly weaker. Perhaps it doesn't give any advantage over determinism for LCLs. All right, that's everything I wanted to say as an overview of our paper. If you find this interesting, I encourage you to read the paper. There is a full version of it on the archive, and it includes a lot more details. In particular, it discusses many more open questions and avenues of further research. Thank you again for watching my presentation. I really hope that we're able to see each other next year at PODC.